First of all, I'd like to thank Piotr and Professor Yao for the kind invitation. Before I start, I hope you get real. Don't expect to see any beautiful pictures or movies at all in this talk. They will be replaced by complicated formula. Unfortunately, this is just my line of research. So I'm going to talk about joint work with Pauline Chen, who's going to speak after this, and St. Yao. So I talk about this problem about quasi-local mass and angular momentum. Although my title suggests conserved quantity, but I think I just focus on these two notions. So the question is actually very simple. So in your space-time, you just take a space-like region. So I'll suppress the dimension by 1. So this surface here represents the 3-dimensional space-time region. And you want to define the mass and angular momentum in terms of the boundary data. So this is your omega here, and this is the boundary which is represented by a curve in this picture. Okay. And at the end, if I have time, I'll talk about other quasi-local conserved quantities and also their limits at special infinity. I'll just focus on special infinity in this talk as total conserved quantities. Okay. So let me formulate this problem of quasi-local mass. So you have a bounded space-time region in a physical space-time, and you want to define the mass or the mass contained in this space-time region in terms of the geometry of this boundary surface. So throughout the talk, I'm going to assume that sigma is a closed space-like two surface, and in fact, we're going to assume that sigma is topologically a sphere. Okay, and the reason why this problem is interesting, I can list a couple of them. So first of all, we know there's no density for gravitation in GR. So in Newtonian gravity, your governing equation is this equation: Laplace phi is equal to 4 pi rho. Rho is the mass density, and phi is the potential. And therefore, if you want to define the total mass of a domain, this 3-dimensional domain in R3, you can simply integrate the mass density. Okay? But notice that because of this equation here, you can actually write this as a boundary integral of this normal flux of phi. In special relativity, you also have a stretch energy tensor as a matter density. And if you want to calculate the total energy intercepted by a space-like region in Minkowski space, and then you can just form this flux integral here, where this u here is the future time-like unit normal of omega, and k is a future unit time-like Killing vector field. And in fact, you can use this formula here to define all conserved quantity simply by replacing this Killing field. For example, if you use a rotation Killing field, you're going to get angular momentum. If you replace by boost vector field, you're going to get center of mass. However, we know in GR, by the equivalence principle, there is no density. And in fact, another difficulty has been touched upon several times this morning, is that because of nonlinear nature of GR, there is no reference or background or fiducial vacuum geometry. Okay. So this reference system has been important in defining any kind of quantity in GR. However, there's just no canonical choice of a reference system. So in our pursuit of this quasi-local mass, we actually come up with a way of finding a rather canonical reference system. So I'll talk about this later. Okay, so I'll talk about this new quasi-local mass that Yao and I defined back in 2009. So this mass actually defined only on these two geometric data. So first of all, you have a surface in your space-time, and we assume the surface is space-like. And therefore, there is an induced Riemannian metric on this 2-dimensional surface. Okay. And the other geometric data is the mean curvature vector field of sigma. So this is not well known in the physics community. So let me just formulate in a way that is probably more familiar. Okay. So how do you define this mean curvature vector field? you can choose two now normals, L and L bar of this space-time, two surfaces. This is codimension 2 situation. And you can somehow normalize it so that L bar is equal to -1. By the way, I'm going to suppress all the space-time index because I have to deal with surface geometry and space-time geometry at the same time. So it will be impossible for me to write out all the indexes here. So this simply means this pairing with respect to the Lorentz metric. Right? And then you can write down this normal vector here. Okay? Where this first one here is just a null expansion with respect to L. And the second one here is just a null expansion with respect to this L bar here. And once you write it out, you notice that this L and L bar here, well, although we have this normalization here, but we know that there's still an ambiguity in defining this. But if you write down this vector here, you notice that this ambiguity, which means you can multiply this L by a positive function and L bar by 1 over this positive function, that ambiguity is actually killed by this expression here. Okay. And in fact, if you're more familiar with Newman-Penrose coefficient, these are just rho and mu here. And in Newman-Penrose coefficient, you know that rho times mu is actually an invariant that is independent of the choice of non-normals. Okay. So we're going to look at this vector field here. And as I mentioned, this definition is actually independent of the choice of non-normals. And in particular, it actually singles out a very distinctive normal direction. Okay, this normal direction later is going to be important in defining this quasi-local mass.
Is this all the local invariance of a two surface in a?
Well, you still have the second fundamental form.
Right, but you're not going to use that.
I'm not going to use it. I'm only going to use a trace of second fundamental form. And in fact, you can see the relevance of this mean curvature vector to gravitational energy since in Penrose's singularity theorem. In that case, if you assume both null expansion is negative, or one is positive, the other is negative, then this singularity formation in the future. So let me just talk about why we consider this distinctive direction and compare this one with some previous known quasi-local mass. So there are actually a few definitions of quasi-local mass. For example, one due to Barnick and one due to Penrose. But let me just focus on these two well-known quasi-local mass, which is more relevant to our discussion here. So first of all, this is a well-known Hawking-Garage mass. And this is defined the following way. You can see that although you're probably more familiar with rho times mu here, but rho times mu, or a multiple rho times mu, is really just the Lorentz norm of the mean curvature vector. Okay, and this sigma here is the area of the surface here. And there's also this one, well, first defined by Brown and York, and then modified by Liu and Yao. So this is Brown-York-Liu-Yao mass. This is defined in the following way. It's 1 over 4 pi. And you can see that this part here is basically integral of the mean curvature, but we have a square here, and this is linear in the mean curvature norm vector. And there's also this first term here, which is actually the reference term. So this reference term is the mean curvature of the isometric embedding of sigma into R3. So you notice that once you pick up your Riemannian metric here, you can ask the question whether you can realize this surface with this given Riemannian metric in R3. And this is so-called isometric embedding problem, which is that's being studied, for example, Nash. But there's actually this theorem of Nirenberg and Pogorelov. It says that if you take any Riemannian metric on your two-dimensional sphere, as long as the Gauss curvature or the scalar curvature for two-dimensional surface is positive, then there is a unique way to isometrically embed into R3. So you're actually going to see a surface whose induced metric is exactly this given metric. Okay, and this uniqueness, of course, is just up to rigid motion. Okay, so this is actually the equation. So you do like dx here, and this is basically the first fundamental form of the surface. That is equal to this given sigma here. And therefore, what you do is you can take the metric here, okay, your sigma, and you do isometric embedding, And because of this uniqueness, you pick out this quantity here, which is associated with your metric, and you can form this expression. Okay. And you can see that the norm of the mean curvature vector appear in both definitions.
What if Gauss curvature is not positive?
There's no uniqueness. Yeah.
So then there's no mass definition?
Well, you can still write down the expression there, okay? But there's ambiguity, and also there's no positivity. The important property of these two mass, the Brownian-Liao mass is a positivity. But there are actually important positivity property of this Brownian-Liao mass. But let me focus on this property. So one of the expected property of quasi-local mass is the following. So you consider a closed embedded surface in R3, in Minkowski space. Well, let's suppose you actually bound the space-time region. Okay. But now this is a configuration where there's no matter field and there's no gravitation. So you expect the quasi-local mass to be equal to 0. Okay. But if you just take this criterion and test on the previous two, the two quasi-local mass definition, there are actually these observations. Okay. So if you take again, I'll suppress the dimension by 1. So this plane here is going to represent an R3. And this is your t-axis, which will represent a Minkowski space. And let's look at these two kinds of surfaces. The first kind of surface are surfaces that are actualizing this R3. Okay? So if you look at this kind of surface, and then you can do a very simple calculation, and that tells you that this this Brownian-Liao mass is always equal to 0. So that's nice. However, if you look at a Hawking mass, a Hawking-Garage mass, that's always strictly negative, unless you have a wrong speed. On the other hand, if you look at the light cone in Minkowski space, and you take another surface that encloses the vertex, and again, this is a simple calculation, okay? And you check that this the Hawking-Garage mass is always equal to 0. However, the Brownian-Liao mass is always strictly positive, unless it is a wrong speed. Okay? So this is actually very interesting if you just look at this these two definitions with respect to these two different kind of configuration. So the new quasi-local mass we defined actually was aiming for this kind of rigidity property. So the one we defined actually, if you evaluate on any surface in the Minkowski space, it's actually going to be equal to 0. In fact, what we have here is that given me this geometric data, so suppose you are physical space-time, and you have a surface here, and then you just give me the induced metric, and also give me the mean curvature vector field. Okay. If this surface were really coming from the Minkowski space-time, there is a canonical procedure to help you find embedding, to realize this surface here in the Minkowski space-time. Okay? So if itself is coming from a reference space-time, it's going to find itself. Otherwise, it's going to find the best match reference space-time. Okay. But I want to actually highlight this part here is among all isometric embedding of sigma into a Minkowski space. I'll actually elaborate this probably later. It turns out there are many different isometric embedding of surface into the Minkowski space, even for round sphere, a perfectly round sphere. Okay, as I mentioned, a new ingredient of the construction is actually to make use of the direction of the mean curvature vector. So how do we make use of it? It turned out this mean curvature vector here is a section of the normal bundle. So we can actually use this one here to define a connection form. Okay? So, so first of all, we assume the mean curvature vector is space-like, and we actually can extract a function. This is a positive function, which is a Lorentz norm. And this basically means that we are slightly away from horizon. And then we can define a connection one form in the following way. Here is J here, is a timeline normal that is perpendicular to your mean curvature vector and has the same norm as h. So it's basically a reflection along the null cone in your normal bundle. Okay. So this is actually one form in your surface. Okay. So this mean curvature vector here was originally a normal vector which rely on the extrinsic space to define it. But somehow, once we extract this the norm and its direction, we're just going to work with this data. So you're given a Riemannian metric on your surface. You're given a positive function, and you're given a one form here. Okay? And from these data here, we can define the quasi-local mass. Okay? And to define this, we actually have to go back to a Hamilton-Jacobi analysis of gravitational action. As you can see, in this, we are going to rely on this reference system. So let me just quickly remind you, this was actually derived by Braun, York, Hawking, Horowitz, and Kijowski. So you start from the Einstein-Hilbert action, okay, and you apply the Hamilton-Jacobi analysis. And in this case, you actually apply to time history of a specially bounded region in space-time. Okay. So this is the best I can do. So Rorman's version of picture. So you apply the Hamilton-Jacobi analysis to the time history of a bounded domain. Okay. And then at the end, just like an ordinary Hamilton-Jacobi analysis, you're going to get a Hamiltonian. And this Hamiltonian is going to be a two-surface integral at a terminal time, okay? Which depend on two vector field, T mu and U mu along sigma. Where T mu here is actually a unit timeline vector. Okay, that's associated with energy. Whenever you talk about energy, you have to fix a unit timeline vector. And this U mu here is a normal vector of sigma. Okay, so this is a picture. You apply to timeline history, you actually get a two-surface integral, which is Hamiltonian, at a terminal time. Okay, and as I say, T mu here is a future timeline unit vector, and so as I mentioned, you actually depend on this T mu and U mu. Maybe let's look at this picture. This is actually better. Okay, so it depends on these two vector field. One is a timeline unit Killing vector field. This is T mu here. Okay, and another one is U mu. This is actually a normal, a future timeline normal vector along this sigma here. So the sigma here is the boundary of the space-time domain. You have U mu here and T mu here. And what you do is you first take this U mu, T mu here. So T mu is not a rest with the surface. So there's actually lapse and a shift vector. So you decompose your T mu into a lapse in this U mu direction and also a shift vector. Okay, and then you form the following expression here. So where N here is a lapse and K here is the mean curvature of sigma with respect to this normal. This U mu here is perpendicular to this. And this V mu here, as I mentioned, is a normal vector here. And this P mu nu minus the trace of P G mu nu is actually the conjugate momentum of this space-time hypersurface here. So, well, apparently you rely on the surface that sigma enclosed, and also the induced metric and P mu nu. But if you look at this one more carefully, it really only depends on these two vector fields. One is this T mu here, and the other is U mu. And the energy is actually defined to be a physical Hamiltonian, the difference between physical Hamiltonian and reference Hamiltonian. And of course, the question is, how do you actually find the reference Hamiltonian? Okay. So supposing the reference Hamiltonian should come from the following data. You should take the time history of the boundary, and you should do isometric embedding into the reference space-time. So this is the configuration that we had. Okay, you should take the time history, which is a three-dimensional time-out hypersurface, and you should do isometric embedding into a reference space-time, and then pick up the reference term. However, if you want to embed a three-dimensional surface into four-dimensional space-time, then this is actually a over-determined system, because for three-dimensional manifold, your metric component, there are 6 of them, but you only have 4 unknowns. Yes?
So originally you just had a two-dimensional surface, right?
Right.
So at the end of the day, why should you care so much about the embedding of this whole three-dimensional surface?
No, well, this is actually, I'm just mentioning this is one approach, but this is the one we're going to abandon.
Oh.
Okay, so instead, so what we did is we don't isometrically embed the whole time history into the reference space. What we did is we're going to look at this terminal surface here. So we're going to take this terminal surface here. We're going to do isometric embedding of this two-dimensional surface into the Minkowski space-time with a matching condition along this normal direction. Okay, so we didn't actually effectively embed the time history, but we did it infinitesimally near the surface. Okay, so let me talk about isometric embedding of sigma into the Minkowski space-time. Okay. So now imagine you just have a surface here, and you try to realize this surface here, which is given maybe abstractly, you're given a metric there. And you want to do isometric embedding into the Minkowski space-time to realize this metric. Okay. And the first thing to notice is the following. Now you're doing embedding of a two-dimensional surface. You recall for two-dimensional surface, there are 3 components of your metric. But you're doing isometric embedding into a 4-dimensional space. Okay. The theorem of Nirenberg-Pogorelov is actually the exact determinant case. You have 3 equations, and you do isometric embedding into a 3-dimensional space. And that's why you expect uniqueness. That's why how they prove the uniqueness. But in this case, you can see that apparently there are 3 equations and 4 unknowns. Okay, because you have 4 coordinate functions in Minkowski space. So the system is actually totally underdetermined. And there is actually one functional degree of freedom. And if we expect any kind of uniqueness, we have to impose an additional equation. Okay? And we actually find this equation through energy. Okay. So let me just say a few words about how to do isometric embedding into the Minkowski space. As I mentioned, you just take your round metric. On a standard 2 sphere, and there are infinitely many ways of doing isometric embedding into the Minkowski space. It's actually quite simple. You take the Minkowski metric in this simple form, and you take your metric, you try to isometric embed. You take any function tau, and you consider sigma plus d tau, tensor with d tau. This is actually just another Riemannian metric because it's always going to be positive definitely in this part. Okay? And then what you do is you just do isometric embedding, apply the theorem that I just mentioned into R3. So this part here is just going to be sigma hat. And then you take the graph of this tau here over the surface. And this one here is going to have this induced metric sigma, just by writing out the Lorentz metric. Okay, so there are infinitely many ways. In fact, not just finite dimensions. It's actually a functional degree of freedom of doing isometric embedding of even the wrong sphere into a Minkowski space-time. This is very different from the the Euclidean space case. Okay, so this is a way of how to. So what we're going to do is we are going to use this tau here, this time function here. Okay, I mean you do isometric embedding here, and you have this tau function here. We're going to take this one here as one function of degree of freedom. So you can imagine you have a lot of round sphere on top of here. They are varying. Metrically, they're perfectly wrong. Okay, but they have some different tau here, and this projection here is again a different surface here. But metrically, they're exactly this wrong metric. Okay. So the way we define energy is the following way. So we take any isometric embedding into the Minkowski space. Okay. And you recall energy is always with respect to some unit timeline vector field. So we just take any T naught, that is future timeline Killing vector field, translating Killing field in Minkowski space. Of course, you can just take your favorite dt is equal to your T naught. And suppose I have isometric embedding here. Okay, and then we just define the quasi-local energy in the following way. Okay, so it's going to be the difference of two Hamiltonians. So this first one here is going to be the physical Hamiltonian. The second one here is going to be the reference Hamiltonian. And you see that we just have to choose this T mu here. You recall T mu is a timeline unit vector field, and U mu is a normal vector field of the surface. So the way we choose it is, well, first of all, in the reference surface case, so this is your isometric embedding. We're going to take this one here as my reference surface. I can just take this T naught here. Okay, so this is my T naught here. Okay, and my U naught of mu is actually very simple. It's actually this T naught mu here. I take its normal part, and I normalize it. Okay, so this is a timeline, future timeline vector field. I restrict to my surface. I take the normal part, and I normalize it, so it's going to be a normal vector field. And how do I choose this T mu and U mu? So these two are going to be vector fields. We stipulates that T mu and T naught mu, they actually have the same lapse and shift with respect to the physical surface and the reference surface. So here I have a physical surface, and I have T mu and U mu here. And here I have a reference surface here, which is inside Minkowski space, and I have this. So the way we choose it is we choose so that this T mu and this T naught mu, they have the same lapse and shift with respect to U mu and U naught mu here. And then when we choose this U mu and U naught mu is the following. We require that the area expansion of the physical surface and reference surface are actually the same along these two directions. Which means if you move the surface in this U mu direction, the area change that you see is the same as the area change that you see when you move the surface in this U mu direction. So this is a matching condition that I talk about. So we actually refer this one here as a canonical gauge. So how much time do I have?
You have 15 minutes with a break.
Okay. However,
Sorry,
well,
question?
yes.
Can we think of that as matching some geometric quantity of the surface in the physical space-time and the surface in the reference
Yeah, that's right. That's exactly what we're doing here. We have a physical surface here, and I have a reference surface here. And the way I choose this normal direction is that so I choose so that if I move in this normal direction, the area change or the area expansion is exactly the same as the area expansion in this direction.
I see.
Yeah, this is the metric condition that we
I
have.
see. Great.
Okay, so this is probably the quasi-local energy in the simplest form. However, we are going to do something with this quasi-local energy. So I'm going to rewrite in a different form, so we can actually work with it. So let me just introduce this new way of writing out the energy, which turned out to be more useful. Okay. And in fact, you also see the dependence on this mean curvature and the connection one fold that is defined. So as I mentioned, I fixed an isometric embedding. So this is my surface here. It is isometric to my physical surface. And I have a T0 here, which is just a Killing field, translating Killing field, future timeline. Okay. Well, first of all, now this is isometric embedding, and this is T0 here. I'm going to define energy with respect to this pair, an isometric embedding and a future timeline Killing vector field. Okay. So it's defined the following way. Well, first of all, we have the reference term. So what is the reference term here? Once we have this T0 here, I can project this surface onto an orthogonal complement of this T0. So this is going to be an R3. Okay. And there is a mean curvature of this surface here. And I'm just going to take the integral of this mean curvature here. And this is going to be the reference term. Okay. And the physical term is actually this term here. Okay. But it's not just about the physical surface. Of course, you can see this H here. That's just a normal of the mean curvature vector. That's a physical surface. And also this alpha H here. That's a connection one form I was talking about. And there's also a theta here that is defined this way. And you also depend on this normal mean curvature. Okay. But you also depend on this tau here. So tau is the time function here. I'm going to consider this tau here as a function defining this two-dimensional surface. Okay. And I'm going to take the gradient of this surface, of this function on the surface, and I form this expression. And I'm going to take the Laplace, I'm going to apply the Laplace Beltrami operator to this tau function here. So this is just a function defined on a two-dimensional surface. So everything here is defined on a two-dimensional surface. Okay. And I form this expression. So it's actually quite complicated, but you recall that we have this is a reference term, and up there we actually use this tau here, and we move back to the physical surface to define the physical term. And why is this term good? It turns out if I check this rigidity property, namely if I take any surface in sigma hat here, okay, and you can see that well, I don't have to take this T0 here. I can take any future timeline vector. And I can do any kind of projection surface. Okay. So this expression here, depend on this T0 here, okay, and because T0 is determining your tau. But no matter which direction I do the projection, this quasi-local energy is always equal to 0. Okay, so you can do one projection, the other projection, and this is always equal to 0. And the reason why this is equal to 0 is actually this following a very simple conservation law. Okay. So if we take this this hypersurface, this is a timeline hypersurface here, and let's call it B. Okay. And then we take this conjugate momentum, okay, which means that this pi here is just pi j, it's just pi j minus minus trace GH of GIJ, whereas GIJ here is the surface of B, so maybe GIJ of B. Okay, and then I indicate integrate this one here on this surface. Okay. But because we're in a vacuum space-time, so the divergence of this pi here is equal to 0, and we're putting in a Killing vector field. So we actually get this integral is equal to 0. But if you write out this integral here, it's exactly this expression. So that's why this is always equal to 0, and it's actually always equal to 0 with respect to any t-node direction. Okay, and we actually prove positivity of this expression. You can see that, well, if you write down an expression that is the sum of squares, it's very easy to prove the positivity. But if you write down an expression that is a difference of two positive quantities, it's much more difficult to prove the positivity. But we were able to prove the positivity of this expression. But you can see that, well, right now we haven't actually anchored this additional functional degree of freedom. As I mentioned, there are infinitely many ways of isometric embedding a surface into the Minkowski space. So what we're going to do is we are actually going to treat this pair, x and tau, x and t naught here. We're going to treat them as an observer. And the expression that we have as an energy. Okay. And in order to get the mass, or the rest mass, we have to minimize the energy among all observers. Okay. And therefore, we just minimize this expression here among all possible pairs. And at the end, we get this desired additional equation. Okay? So this is actually Euler-Lagrange equation of this quasi-local energy here. Okay? And we have this one from isometric embedding. And you recall there are actually three equations here. And we get an additional one, which is the Euler-Lagrange equation. So altogether, there are 4 equations for 4 unknown. So I'm going to show you what is this J here in the next slide. Okay. But somehow you can actually write down this, when you write down this expression, you can check that this equation here is again an equation that is actually identity with respect to any time-line Killing vector field. Okay. And it turns out this quasi-local energy can actually be written down in a easier way. So if you actually have a critical point of this quasi-local energy, okay, which means that this equation here is satisfied, then the quasi-local energy, the expression that I wrote down before, actually has a very simple expression. So it's just the integral of this rho here, where this rho here is just this expression. Okay, so you see that this involved. This is actually the mean curvature, the normal mean curvature vector of this reference surface in the Minkowski space. And this is a physical one, and this tau here are the time function. And we also get a quasi-local momentum density. That is this expression. This is a J over there. So you can see that you involve this rho here, which is defined this way, and you also involve this alpha of h naught and alpha of h. But the optimal isometric embedding equation is just the divergence of this J, which is a 1/4, is equal to 0. So from here you see that once we have a critical point, it means that we actually have a surface in the Minkowski space. Okay. And also we acquire this two important quantity. This is what we call the mass density. This is defined along the two-dimensional surface. And we also have a 1/4 that is defined on a two-dimensional surface. And the equation is just this 1/4 is divergence free. Okay, and then we can go ahead to define quasi-local conserved quantity. Okay, well, you recall that before our problem is that we don't have any density to integrate, and we don't have any Killing vector field. But now you see that well, I have a physical surface here. Suppose I have a surface here that is optimal isometric embedding, and I have a surface in the Minkowski space. Then I can actually use this reference surface here to transplant any Killing vector field in the Minkowski space. Okay, and I also can make use of this rho here and J here, the two density functions, to define quasi-local conserved quantities. So this is the expression of the quasi-local conserved quantity. So what you do is here is you take a Killing field in the Minkowski space-time. You call it 10-dimensional of them, and then you pair this one with your T naught, okay, and then you also take the tangential part of this surface here. So this actually defines the linear momentum if you use a spectral translating, or angular momentum if you use a rotation, or center of mass if you use the Booth spectral field. And not only we have this positivity, but we also have this minimizing property of a critical point. Namely, when this quasi-local mass density is positive, then we can show that this critical point here is actually energy minimizing and is also locally unique. Okay, so since I'm short of time, I was hoping to talk about this special positivity. So it turns out this not only this satisfy the condition that for any surface in Minkowski space, the energy is, the mass is equal to 0. But in fact, this positivity property allows us to solve this this equation. So maybe I can make it short here. So although this is actually a quite complicated looking equation, but in many cases we were able to solve it. So in particular, we can use this one here to define total conserved quantity as special infinity. Okay? So for example, consider asymptotic flat initial data set. Okay, with this is 3-dimensional space-out hypersurface, and you consider the coordinate sphere. So this is in the ADM setting. Okay, and as long as the ADM mass of this initial data set is positive, then we can solve the optimized isometric embedding of each of the coordinate sphere, and that's actually unique. Okay? So that actually allows us to calculate this this quasi-local conserved quantity, and we can actually take a limit to infinity, and that actually define this full set of conserved quantity. And this E and PI, they're the same as ADM energy momentum, and JI and CI, they correspond to the total angular momentum and total center of mass. And they are somehow different from the traditional definition. Yes. Okay. So let me, So I think I should finish off. I'll talk about some properties of these total conserved quantities. So these total conserved quantities, they only depend on the geometric data and the formulation of the surface. So in particular, it doesn't depend on any asymptotic flat coordinate system or the existence of asymptotic heating field. In defining, for example, angular momentum or center of mass, you really rely on this asymptotic heating field. And all these total conserved quantities vanishes on any space hypersurface in the Minkowski space, regardless of the asymptotic behavior. Okay. We're actually somehow very used to the fact that I naught special infinity is just a point in the Penrose diagram. But I want to remind you, I know it's not just a point in the physical space-time. I mean, you can have space-time hypersurface like going out to infinity in very, very different way. Okay? And in fact, this actually provides a very nice testing ground for our quasi-local mass. We can show that in other cases when previous definition doesn't work. This actually gives you a very nice definition. For example, we prove this invariance of total angular momentum theorem. So you can take basically any, in the Kerr space-time, take any strictly space-time hypersurface and take our definition of total angular momentum, and it's always a constant. While if you just take other, for example, ADN definition, you're going to see some pathological examples. And also this center of mass actually satisfies this nice formula, which is essentially the P equal NV formula for Beckett-Einstein equation. So let me just summarize in the last page. Okay? So what we did is basically a very precise way of measuring gravitational energy. You can see that we always have this rigidity property in mind, and conserved quantity, and apply to a strong field regime. And this approach here not only define conserved quantities, but you also sort of anchor a canonical reference system through this optimized isometric embedding system. So we actually get a sort of a best match of a surface in the Minkowski space, and then you can just compute whatever conserved quantity you want to know, by comparing these two surfaces. Okay. And recently, we were able to extend this construction to allow de Sitter or anti-de Sitter space-time as a reference. Okay? In a way that now you give me a physical two-dimensional surface, I'll be able to find the best match in ADS space-time, ADS space-time. In fact, I believe we can. We also did it the Schwarzschild case. Okay, and we think the curved space-time is also doable. Okay, so you can imagine a situation when this becomes quite useful. Well, we know the no-hair theorem. So black hole is unique, but in reality, every black hole is just perturbation of pair of Schwarzschild. Okay, now suppose you have a space-time here. And you have a perturbation. And suppose I have a surface here, two-dimensional surface in this perturbed space-time. Now there are two possibilities. Well, this space-time here may be just purely a diffeomorphism, maybe purely a gauge change. It's exactly the same as the original, but because you use a different coordinate system, we will not be able to recognize it as the original space-time. For the procedure that we had there, we actually give you a canonical procedure to find the embedding of this into the original space-time here. Okay? And if it's actually an actual perturbation, then we're going to produce a family of surfaces in between. That is basically the best match of the original one. In fact, that's going to be the topic of Pauling's talk about this application of this quasi-local mass in gravitational perturbation. Yeah, but so far, well, it works out very nice in a lot of perturbative configuration, because I talk about special infinity or null infinity or a small sphere limit. Basically, the knowledge that we know about this optimal isometric embedding equation already allow us to solve this equation uniquely in many cases. So this is actually most powerful in providing the fine-tuning in any kind of perturbative configuration. We expect more application can be found when we have an even better understanding of this the mathematical theory. So I think I'll just stop.
Thank you very much. So we knew that we had to be able to associate a positive energy to any cut on scry or its spatial infinity. Otherwise, general relativity would be inconsistent. But why did there? I mean, was there any a priori reason to think that a positive quantity with all the properties that you list should be associated with a generic surface in a space-time? I can't think of any physical reason why we should have expected that in advance.
Well, I guess
Is there any physical or mathematical reason?
I thought the same scenario applied to when positive mass theorem was actually proved. I mean, no.
If the positive energy theorem had not been proven, general relativity would be wrong. It would be inconsistent. The vacuum would be unstable.
Well, I guess.
But I don't see any need in general relativity for there to be, for the consistency of general relativity, for there to be a positive quantity associated with a generic surface. There's no.
Well, I didn't actually talk about this positivity theory, and I don't think this is actually generic. I think, well, in the positivity theory, we have to assume that this is actually the surface is basically convex in some sense. I think you can consider some, I mean, if you expect any kind of subadditive property that is true for mass of energy, then you will probably have to assume that it has a certain kind of convexity property. I mean, this is, I mean, to us, this is a limitation of technology, but maybe at the end, this is true. I mean, you have something that is true in the total case, for total energy, and if it's actually close to that, it's enough convex, then it's also true.
So what you're saying, if it's not convex, then maybe the energy would be negative.
But I don't even see why there had to be a positive energy associated even when it is convex.
Well, we know this is true at special infinity. We know this is true at null infinity.
It's a very special case, right? Co-dimension.
Well, it's still associated with the it's still a flux integral. I mean, in all cases, the bounded mass, the ADM mass, they're all sort of a quasi-local quantity, like flux integral type.
So what you're saying, it's very surprising that it works.
I mean, I don't think if there hadn't been the physical argument that general relativity would be inconsistent
Yeah.
if the bonding mass were not positive. I mean, Yao can speak for himself, but I don't think he would have spent all those years trying to prove it if there wasn't a really good reason to think it had to be true.
Yeah.
It
But it's
doesn't look obviously true from the equations, but
Yeah.
but this, I don't see why.
But
what
this
the problem would have
possibility
been.
is actually very important to us. I mean, without this, we cannot solve this equation. Basically, the solvability of this optimal isometric embedding equation comes from positivity. Yeah. So I mean.
Other questions or comments?
I'd like to add that it wouldn't be dynamically unstable. It's the evolution equation. So in Minkowski spacetime, you can still, in a certain sense, solve the evolution equations with initial data with negative mass. There are no such data, but there's a small data global existence theorem that would work, even if the mass were negative. So the instability that you're talking about, whatever you mean, I'm not sure, but it's not dynamic instability.
But this is a quasi-local
what I mean
configuration.
would be
There's
there
just
would
no
There would be
well-defined boundary
infinitely
condition.
many configurations with, if the energy could be negative for some isolated system, then there would be infinitely many configurations with zero energy, that with non-zero curvature, and there would be no vacuum. There would be no control over the vacuum.
Which would worry you.
Everything would
I
be
mean, maybe
unstable.
it won't worry classical physicists.
Oh, it would be a classical problem. Yeah, it would be horrible. It would be a terrible classical problem. So, yeah.
Okay, okay. Well, thanks again. So we're starting again at 4.
And it doesn't have a general. You're not going to get positive.
Oh, right, okay.
Right, but
They're restricting the one class where they're able to prove that she did.
yeah. Well, why should it have worked? There should be some simple reason.
I'm tired of that, but yeah, so sure. I mean, it's
Well, I think what I meant is before the proof you expect it's true, but gravitational energy can be negative. You don't really expect it.
I don't know why you expect it